So this is 6.1 continued. We're going to look at proving trig identities a little more in depth. So what does it mean to prove a trig identity? It means you start with one side of the identity and you change it until it equals the other side of the identity. Also remember that an identity is an equation that's always true. So it's already been proven to work for every possible situation. So here are some tricks. Always start with the more complicated side. Always check then if the equation can be factored. If it can be factored, factor it. If there's brackets, try to eliminate the brackets by foiling or multiplying things in. You can get a common denominator if things are written as fractions. If you have a single term denominator and lots of terms above, you can try separating them, and I'll show you an example like that today. Number 6 says if there are squares involved, think about the Pythagorean identity. So anytime you see the squares, we jump right to that green sheet with the Pythagorean identities. If all else fails, turn everything into sine and cosine, and always keep checking on the other side of the equation. So always keep checking what you're trying to get your answer to be, because then that might help you think, okay, I need to change this somehow into this, and then it'll help guide you. So for question 9, we want to make cotan times sine the same as cosine. So when I look at that, I don't see much that I can do so far, besides make cotan into cosine over sine. So if you look at your identity sheet, we see that cotan is cosine theta over sine theta, and then that's multiplied by sine theta. Now, when you have a sine theta being multiplied and a sine theta being divided, you can cancel them out because they're inverse operations. And then that leaves us with cosine theta, which is the same as the other side. So we'd say cosine theta equals cosine theta, and then remember you finish off every proof with QED. Basically means the end or the proof has been finished. So one of our identities says sine squared plus cos squared equals 1. So if I just want the sine squared by itself, I can move the cos squared to the other side. Remember, you are allowed to manipulate the identities, but you're not allowed to manipulate both sides of the proof. So if I subtract the cos squared to the other side, we get that sine squared equals 1 subtract cos squared. So I can trade the sine squared here in my question with 1 subtract cos squared. So we get 3 subtract 1 subtract cos squared, and that's going to equal over here the right-hand side. Now this negative can go into my brackets, because remember you don't actually want brackets in your other side. So let's get rid of it by multiplying that negative in. So we get 3 subtract 1 plus cos squared theta. And when you go to your 3 minus 1, you get 2 plus cos squared theta, which does equal the right-hand side. So we'd say QED, the question has been finished. So this question we're asking something a little bit different. We're trying to find which one of these, sine, cotan, tan, or minus cosine, is our answer if we simplify this expression. So we can see that the bottom is 1 minus sine squared theta. And remember that sine squared plus cos squared equals 1. And so if I subtract the sine to the other side, that means that cos squared equals 1 minus sine squared. So I can trade 1 minus sine squared for cos squared because of that identity, that Pythagorean identity. So when I switch it, we end up with sine times cos divided by cos squared. Where can we go from here? Divide a cosine out, right? So here there's a cos on the bottom, and cos squared means there's actually cos times cos on the bottom. So there's like cos on the bottom. So usually what I do is I just cancel out the squared, because now if you divide out a cosine, there's not a cosine squared on the bottom. There's just a single cosine left. So that leaves us with sine theta over cos theta, and sine over cos, yes, is tan. So my answer here is that tan is the simplified form of this equation. Okay, so for this one, we're looking for the non-permissible values in degrees of the equation. So I see here that in my denominator is sine. So this means that sine theta cannot equal 0. So let's look on our unit circle. Look on your unit circle, and let's see, where does sine equal 0? Well, sine equals 0 at 0 degrees and at 180 degrees. So So we'd say 0 degrees and 180 degrees are non-permissible values for this question. Again, 0 degrees and 180 degrees because that is where the denominator would equal 0. And here's what's tricky. Is there another denominator in this question?
What?
Yeah, there would be one.
So since tan is actually sine over cosine, then cosine cannot equal 0 either, because that's another spot where we'd be dividing by 0. So if we look on our unit circle, we see that at 90 degrees and at 270 degrees, cosine would be 0. So I actually also have to include 90 degrees and 270 degrees into my list of non-permissible values. So again, non-permissible values are whatever equals, wherever the denominator equals 0. Now part B says verify that theta equals 60 degrees and theta equals pi over 4 are solutions to the equation. So that means I'm going to do the 60 degrees first. If I plug in 60 into my equation, we get secant at 60 degrees equals tan at 60 degrees over sine at 60 degrees. Okay, now at this point, you figure out that these are equal by looking on your unit circle and taking the exact values. So secant at 60 degrees, you look on your circle, secant at 60 degrees is the reciprocal of cosine. So that means that secant is 2 over 1 at 60 degrees. Tan at 60 degrees is root 3 over 1. And sine at 60 degrees is root 3 over 2. So we have to simplify this now. If I divide root 3 over 1 by root 3 over 2, that's the same as multiplying by 2 over root 3. My roots cancel, so I get 2 over 1. So this has showed that at 60 degrees, this identity is true. So let's take a minute to practice this. It's on page 296, number 1, 3, 4, 7, and 12. And then on the back of your handout, there are 3 trig proofs that we're going to do as well.